off we go. So we learned a bunch of cool different ways to visualize things. We made some pretty graphs last time. We learned about when we plot numerical variables, numerical values. We could either do a line plot, that's where the dots are arranged in an order, and usually there's some chronology to it. Like that's the reason you'd want to fill in the gaps. But when you don't have any sort of chronology, you just want to graph x's and y's, you can do a scatter plot. So scatter plot just puts a dot where there's an xy value, and you pick which values to be your x and which values to be your y from your data set, and each row gets to be a little dot on your table. So that's scatter plots. Line plots for numerical things. For categorical things, you have to turn words kind of into numbers. And so a common way of doing that is to like count how many you have. Use a different number associated with that categorical variable. So like how many chocolates were in my data set? How many strawberries? Like count and give it a number. That would work. So that was bar charts. And at the very end, we talked about things called histograms, and that's where I want to spend most of our time today. All right. So a histogram, the idea of it is I've got a bunch of numerical values, like these, for example, and they're never going to be the exact same numbers. Like I'm never going to see like 188 ever again, but I might see values close to it, right? I might see 189 like that, right? I might see values close to it, and I want to know for different chunks of ranges throughout my data set, how many things are like big, how many things are small. Maybe let's do chunks of 5. That's what I did in this example. All right, I hope that is coming back to us. So chunks of 5, that's one way to do it. And this is called binning. Binning generates a histogram eventually. All right, so binning is just the idea of like we've got some numerical values. They're never going to be exactly equal to each other, but we can shove them into bins and count ones that are in the same bins. Like the 188 and the 189, those can fit in the 185 to 190 bin because it's going by 5. So we chose to go by 5s. All right, but do remember the endpoints are very important here. There is a 185, when it's a 185 to 190 bin, that means that what goes in this bin are all the values between 185 and 189.99999. So that means you're not including the endpoint. The endpoint would go in the next one. So like we did have 185 here. That one went in this one, not this one. Does that make sense? Is that coming back to us? Questions about that? So that's what binning means, and that's just very technical, I know, but the endpoint, the right endpoint, is not included in the bin. All right, it's just like the A range stuff for arrays. So that was the 180 to 185, but not including 185 bin. The 185 went in this one. It was one of those lines. And so if you draw lines like this, you can get a feel for the distribution of this data. How is it distributed among these different bins and these different values? All right, and that leads into the idea of histogram. So a histogram is just doing that, drawing those lines, but with, and we're filling them in, right? We're making an area. So a histogram gives you the distribution of your numerical thing, and for every bin, like this was the 300 to 400 bin, but not including 400, you can get you draw a little bar, and that bar, the area of the bar, tells you how many things proportionally are in that bin compared to others. So most of the movies we were talking about were between $300 and $400 million in the revenue that they made. And the next most populous bin was this one, right? 500 to 600. And it's the area that tells you the proportion, okay? So the area of each bar is the percent of individuals in the corresponding bin. And that's why when we generate histograms, it by default puts on the y-axis percent per whatever your variable was. It's very confusing. And so I want to talk about that, like hopefully the words here make a little bit of sense, but I want to talk about this weird unit on the y-axis today. All right. So we made this histogram last time, and the way we did it was like this. Let me run this cell so we can do other stuff. Okay, it's happy. Whee. Oh. It's thinking about it. There we go, way down there. All right. So we made it like this, and we had a data set that looked like this. We said this was our millions of dollars, and there we go. The movie, and then how much money it made. And we binned those based on a set of bins in this order, 300 to 400, 400 to 500. So we set our bins this way by making an array, and this is the way you can make a histogram. You say, all right, I want to make a histogram of all the adjusted gross values for this table, and I would like to use these exact bins where I made that array from 300, 400, 500, all the way to 1800, because that was a little bigger than what I needed. And all those adjacent values in that array gave me my bins. This meant, like, generating this array meant I'm getting a 300 to 400 bin, that's the first one. A 400 to 500 bin is the second one. Can you kind of read that? It's a little odd, but that's the way that Python wants it, and the library wants it. And then you say unit, $1 million, and that's what goes on the x-axis. And then the y-axis, it was saying percent per $1 million. And it looks like it was about 0.4-ish for that 300 to 400 bin, all right? 0.4% per $1 million. That's a really weird number, I think you can imagine. It's not like 40%. It's 0.4%. That's odd. So let's explain that now. All right, so it goes back to this idea that we're going to use area and double the area when we have double the amount of things, not like quadruple it. Don't just double the width or something. Just this idea all over again. So, okay, height measures density. How much stuff is in this bit of proportionally this bit of the table, all right? So that means then, we've said this already. Here's some equations. We're going to have to get there. I'm sorry. I'll put this picture back here, actually. I think that would help. So here is our histogram. Put it in the corner, maybe. There. So let's look at it this way. So height measures density. That means what we're doing is the area of the bar is the percentage of those values relatively in that bin. All right. And how do you get the area? That's just the width times the height. We have kind of hard-coded the width of this bin right now. It is width 100, right? They're all width 100, aren't they? Okay, so it's $100 million per thing. So that's that. And that means the height of the bin, if you solve for it, right, the area and the percent and the width times the height, if you solve this equation for the height, you divide by the width, right? The height equals percent over the width, right? It's going on the bottom there. So that means your height units are the percent of the values that are in the bin over the width of the bin. And so those units become percent per unit of width. All right? Disgusting. And so that's why we see percent per $1 million. That's all. All right? So the height measures the percent of the data in that bin relative to the amount of space in the bin. That's what the book says. All right? So the height of your histogram bars measure proportionally how much stuff is in that bin compared to others. All right, so that's why we see percent per $1 million. So that kind of makes sense, right? Because there's, let's try to solve for this maybe. Dun, dun, dun. 400, there were, I think that's something I could do right now. Let's solve for that. Let's try to calculate that height just by ourselves. Let's get that 0.4. All right, so here is our histogram. Let's go back to it and let's do it this way. So let's calculate the height of the, I don't know, this one's 0.4, that one's like 0.25. Let's do the 400 to 500 bin. Why not? Of the 400 to 500 bin. All right, and so let's figure out the percentage, the width, and the height. All right, so we did the binning. The binning is like this. The 400 to 500 bin has 52 things in it, 52 elements relatively, okay? 52 things in it, 52 values, 52 movies. So the percentage then of the things that are in that bin relative to the rest is 52 over how many things are in this table, like all these things that could go in any bin, like the sum of all of these, which is just everything in the table. Just every single movie ever. There were 52 movies in the 400 to 500 bin, but how many movies were there in total? It's just like how many rows were there in the millions table. So the percentage is, oops. Oh, I have to re-include all this. Excuse me. I'm going to have to rerun all these lines, I think. I have to include top. Oh, no. Here, let me just restart. If you want to run all the cells really quick, it's kernel, restart kernel, and run all cells. Let's just do that. because then it'll work for me. Slowly but surely. There we go. All right, so the percentage then, the percentage of the values that were in the 400 to 500 bin, it was 26%, 0.26. 26% of the values were in this bin right here. 26%, all right? So we're getting close, 26%. And then we want, right, we want to solve for the height, all right? The width is always, well, we want to do the percentage for real, like it's times 100, right? So it's 26% of the values were within that bin. And then the width of the bin, right? The width of the bin was always the same. It was 400 to 500, 300 to 400. It was always 100. The width was always 100. So 100. And so we're solving for the height. It's the percentage over the width. So percentage, which is 26 over the width, 0.26. And that's why we see this exact value, 0.26% per $1 million. Does that make a little bit of sense now? It's very weird. I must say, but there's a big reason why we're doing this. So that's how you find this height, and that's why those units are so weird. It's because we're using area, relative area, to do things. Okay, so yeah, I think that is most of what I wanted to say. Yeah, this is how you solve for it. So if you're ever asked a question about histograms, let's bring this one back down so we can look at it and our calculations together. That's what we just did. We found this one, 0.26%, and you can do the same thing for the other ones and figure out why they were drawn that way. Yeah, if you're ever asked the question, like, how many people are in the bin, like, how many individuals are in this particular bin, you go and you look at the areas, all right? How many individuals are in this bin relative to others? You look at the areas, because that's what that tells you. And then if you're ever asked, like, how crowded is the bin? How many people are in that one? Just that one by itself. Then you can look at the height, because what does the height tell you? Percentage over the width, all right? The height tells you the percent of data in the bin relative to the amount of size of that bin, okay? So it's a little weird, but area for number of things, height for how crowded it is, and I'm going to give you a good example in a second, so I hope that will help. Let's see here. Yeah, let's pretend that I've given you a question, all right? I'm going to give you one, and then I want to show you why we care about this. Gosh, do I want to do that now or later? No, I'm going to give you a question in a second, but let me give an example first. All right, so the whole reason we're doing this area business is because you could make some weird looking bins, all right? Let's say we made some weird uneven bins instead. Let's do it this way. Let's say instead of the nice even bins that look like this, like by 100s exactly always, let's make some bins like this. Let's just make an array. It's got to go between like 300 and 1800 still. But let's make this array. Like these are going to be my bins. 300, 350, 400, 500, and then all the way to 1800 immediately. All right. So that means I'm making 1, 2, 3, 4 bins. I'm about to make 4 bins, but the first one's 50 width. The second one is 50 width. The third one is 100 width. And then the last one is like 1300 width. They're not the same size. All right. And so what's going to happen is some weird things. All right. So I want to make a histogram with those bins instead. All right. I'd like to make a histogram with those bins instead. I'll call these uneven bins. So make a histogram with those uneven bins. And let's just do the binning first. So relatively, what's in there? I don't need the unit here. If I use these uneven bins, you'll see that there's a ton of movies between the 1500 and 1800, right? There's 67, that's the most, because there's so many things within that range, right? It's a giant range, 1300 wide relative to all the others. So this 1500 to 1800 bin is very, very wide, but it also has a lot of things in it, all right? So the area should still be a bit small, though, when we do the histogram because it's so wide. Let's talk about that. So bins equals uneven. Unit is still millions of dollars. Here, oh, sorry, I want the histogram. .hist for histogram. This is what we see now. It's very weird and extended. So you see how these two are the same size. This one's a little bit extended. That one's even more extended. But this one's very low, even though there's more things in it. You see that? 67. But if you look at the areas, it checks out. The area of this is the biggest area, but you can tell that it's very similar to this size because it has almost the same number of things in it, area-wise. That's why we did areas. Because if we didn't do areas, if we just did like 32 on that bar, height 49, height 52, height 67 for the next one, I can simulate that with this idea. This is not a true histogram I'm about to make. You say, this is just for educational purposes. Normed equals false. This is what would happen if you did it the other way. You see it? You would accidentally think like there's a million movies between 1500 and 1800 if you didn't use the area. That's the moral of the story. That's all I'm trying to say right now. Does that make a little bit of sense? So if we didn't use the area relatively, we'd be like, all right, yeah, the height of this last bar from 500 to 1800 is 67, and now suddenly you think there's like 12 times as many as there were in the previous bar, 12 times as many movies over here. Because as humans, we see area and we think, all right, the area's been like quadrupled, then there must be 4 times the amount of movies. But no. This is the true one based on area. You can see it's just a wide range and it's still pretty sparse. It's just as many things almost as this bar because of the area. Okay, so that's why we make histograms in that way. Does that make sense? We use that area principle. Okay. Yeah, I think let me prove to you how we count these things, and then we'll talk about some more stuff. All right, so this is the good one, right? This is the bad one. This is the normal way to make with those uneven bins, the way that it works. So let's take these bins, those uneven bins, and we'll move it around. All right, so I guess I'll put it in this order. That's the weird way. This is the normal way. And so here are the bins that generated this histogram. And let's call those something. Let's relabel the adjusted gross count to just count because it's easier for me to type that way. What else? Let's do that. So now it's just called bin and count. And then what do I want to do? I'll call these, let's call this histogram elements because I want to do some math and I'll give it a name first. Histogram elements gives me that. Yeah, so that's my table. And let's just programmatically figure out these heights together. Okay, let's figure out those heights together. So let's do it this way. So what I need is I need to know, because it's always like proportional, 32 over all of these, the amounts of all of these, 49 over all of these. So I need the sum of the count column. That's the total count. So I want proportions, I want percentage. So it's the histogram elements column called count. And I'd like the sum of all of those. So total count. So I'll always be dividing by that. So there's 200 things total. Now we know. And then I want to get the percentages for each of those counts because I'll divide them by the total count. So histogram elements dot column count now over the total count times 100 for percentages. So now the way that this works is now you see that the first bin had 16% of the values. The second bin had 24.5% of the values. The third bin had 26% of the values, and the fourth bin had 33.5% of the values. Do you see how I'm calculating that? Does that make sense? So we're close, right? So we have percentages now, but the area of the bar that we're about to draw for each of these, it is that percentage, but we've also chosen weird different widths for all of these bins. So now we're going to have to do some division to see how high each of those bars should be. Okay, so we'll figure that out together now. So those are my percents. I'll call that percents. And then let's add that to the end of this histogram elements table. I'll say with a column called percent. I'll put the percents there. Oops, percents. So now I tacked on this percent column. So 32 was the count, but it was really 16%. 49 was the count, but relatively it was 24.5% of the values in the 350 to 400 bin. So that's how we got those numbers. And then we're getting so close. Let's just call that histogram elements. I'll just attach it like that. So I'm modifying the table now by sending it back into it. And now I want to know, I need to get the widths of all these bins, right? This bin, 300 to 350, the width of that bin is 50, right? The width of the 350 to 400 bin is 50. The width of the 400 to 500 bin is 100. The width of the 500 to the 1800 is 1300. So let's calculate programmatically those widths so you see what's happening under the hood by Python when it's doing this histogram drawing. So I need to figure out the widths of all those bins, and one cute way to do it is you get the histogram elements.column, you get the bin column, and I showed you this very briefly. I kind of want to subtract these two from each other, all the adjacent values I want to subtract from each other. And there's a nice function in the NumPy library, it's called np.diff, that does that for me. So there it is. There's the widths of all those bins, and that's why they're next to each other like that. So let's call that bin widths. There's that. And then the number of bins, remember the way that this works is the last one is 500 to 1800. There's really 1, 2, 3, 4 bins, even though there's 5 elements in this table. So the number of bins that I'm working with is histogram elements.numRows -1. And what I'd like to do is for each bin, let's say histogram elements, let's take just the first 4 of them because the last, I can't, like if I want to attach the bin widths, I don't have a value for the last one. So let's just take the first 4, np.arange, give me the indices num bin, so that's 0 through 3, give me the first 4, indices 0 through 3, that looks like this, just I've taken the first 4, indices 0 through 3 with that arange there. And then I want to add the width column, and I'll attach the bin widths. So width column, and I'll call it width of each bin, and bin widths can go there. There we go. I think that's what I wanted. Okay, so this is what Python does every time you're trying to make a histogram. So this bin, 300 to 350, there were 32 values in it. It was 16% relatively of all the other values. Its width is 50. There's 50 things between 300 and 350, right? That's the width of it as we're drawing it. All right, the width of the last one, 500 to 1800, was very wide. So that's how we can calculate that. Let's just attach that to the histogram elements table by assigning it back in. So there it is. And then if I say, oh gosh. I just want to print it back out. Boop. Let's pretend that happened in that order. So there it is. There's the my table again. And so now I've got that exactly called histogram elements. And now I want to calculate the heights. Finally, I've got the width of the bin. I've got the percent in the bin. I can do the division to figure out the height of each of these values that needs to happen if I'm going to draw this histogram myself. And that's what Python's doing secretly for you, right? So the heights, that is equal to, you take the percent column, right? The height is equal to the percent over the width. You draw it just like that. Height is equal to percent over width. So it's equal to the histogram elements.column percent over all the values in the width column. There we go. All right, so those are my heights. And this last one is very long. Let's round that. So you can say heights is not just that, but let's do np.round, this array that's resulting from this. Round it to 2. I'm just going to use a bunch of lines to make it pretty. So those are my heights now. All these values. Those are the heights of the bars on my histograms. And for fun, let's attach that heights to the end of each of these. Let's add one last column to histogram elements. With a column, height, and that's my heights. So that is what Python's doing as it's calculating the heights of all these histograms, and that's why we saw exactly this one. And now we can just read it off finally, and it's happy. All right, so I hope you kind of followed a little bit of that. So I wanted to go the other direction. There we go. So now we know for sure why this first bar, the 300 to 350 bin, its height in the graph we found it needed to be 0.32% per $1 million. The next one, from 350 to 400, it was a bit higher, right? It's 0.49. 0.49% per $1 million. That was the area that we solved for that we needed. That's relative properly. Then the next one, that was a width 100 bin. It was between 400 to 500, and its height was 26. It had 26% of the data, and it's 0.26% per $1 million. And the last one, even though it had a lot of things, it had the largest percent of things because it was so wide, and we're using area to say how much is in there. It was the shortest one. It was the shortest bar because we don't want to accidentally make people think there were more things than there were in it. The height's going to be 0.03% per $1 million because even though there were a lot of things in it, it was also very wide. If we're using area to say how much is there, just solving for how high it needs to be to keep the area proper and relative, it needs to be a very, very short bar if it's so long. All right. And so that's why we have those values, and that's why we use those units. Does that make sense? Are there any questions about that? There's a lot there, I know. So, yeah, now we can come back to the slide and it should make more sense. So if you're asking, like, how many people are in this bin relatively to each other, you use the area. How many individuals are in this bin, you use the area. Like, you can see that these two bars are about the same. There are probably about as many people in each of those. And it makes sense. The counts were very similar. 52, 67. Same with these guys, 49, 52. If you actually compared areas, these two are about the same in terms of area, so they had about the same amount of people in those bins. All right. So you're using area to count how many individuals are in that bin. But if you want to know how crowded the bin is, how many people are in it relative to its size, then you use the height finally. So you can see because this bar is so low, this is not a very crowded bin. There weren't a lot of people all spaced out between it. But you can see that there were more. Look at these two bins, they had the same width. There were more, this one's more crowded than this one. There's the same amount of width of the bin, but this one's more crowded because it was higher. You can see immediately that it had more people in it because of that. It's more crowded, there were more people packed into that bin when it's higher. It's easier to see when they're the same size. But that's what that means. Crowdedness is height, because that tells you how packed it was. Okay, so I think that's most of what I wanted to say, and I hope you can see why we use those to answer those questions now. Yeah? Are you ready to try? I want to give you a graph, and I want you to interpret it. All right, so with this idea in mind, I'd like you to try it. You can just discuss with your neighbors, but I have some questions to ask you. I'd like you to think about them, and you don't have to write them down anywhere, but I'd like you to imagine. I've got a histogram that I've made with some weird bin sizes, like maybe some people's ages, how many people are in a group, or I guess the age of movies maybe, how old are they and how many were in the data set based on how old they were relatively. So it doesn't really matter, but this is a histogram. It's got some weird sized bins that are not all the same. I'd like you to look at these two bins, 10 to 20 and 20 to 40. So that's this one and this one, all right? Those are the two bins I want you to look at. My question to you is, which of those has more movies in it? If I'm using movies here, this is a number of movies. Which of these bins has more movies in it? And then which of these bins is packed more? Which of those is more crowded with movies? Do you understand the question? So try to use those ideas to answer those. Think about it. You can discuss with your neighbors if you'd like, and we'll come back and discuss it. You don't have to write the answer down. I just want you to think about the answer. Remember, the height is percent per unit of width, which is very odd. How many things are in it over how wide was it? And so that means it's more crowded when it's something, right? More crowded if there's more things in it and it's squished. They're all squished together in a small bin. That's going to change the height in a certain direction. All right, have you thought about it? Dun, dun, dun. So, would a brave soul like to tell me what you came up with? Which of these bins is going to have more movies, do we think? Any thoughts? Or we're only looking at these two guys. Which one has more stuff in it? Yeah, and you use the area to figure that out, right? We notice that, all right, there's more things in it relatively. If the area is bigger, it looks like there's almost double the amount, if you can compare that way. Not quite, maybe 1.5 times, but there are more things in it. The area is bigger. That means proportionally, we're using area to tell how much stuff is in it relative to other things. And so because the area is bigger, that means there's more things in it. Good. There's that one. And yeah, because it has a bigger area. And then how crowded depends on the height, right? If the height is taller, that means there's more stuff packed into that smaller bin. Even though there were fewer things in the 10 to 20 bin, you see that it's taller though. So there are more things relatively per unit of width. That's the reason the height got taller. Does that make sense? That's the reason the height got taller, given that that formula, and that's why the 10 to 20 bin, the other one, because it's taller, that means it's more crowded. It doesn't mean that it has more things in it. It means that the things that are in it are packed tighter together. There's more of them relative to the amount of area we're using for that bin. The width of that bin, the space that we're holding for that bin. Okay? And yeah, I know this is very, very technical, but this is the reason we make histograms in this exact way so we don't run into this weird problem of like, oh yeah, this is supposed to mean 70% more. No, we don't see it like that as humans. So we're trying to be very careful so that we don't mislead people. Okay? And yeah, that's histograms in a nutshell. There's some weird technical details to it, but you can kind of see how to read them now, I hope, and you know how to make them with the table .hist function. And I think you're good to go. Are there any questions about histograms, just the basics of them? Kind of see the vision, where we're going with them? They tell you how packed things are in a certain range. That's all we really see. Okay? And so we do have, though, bar charts as well. Those look like sideways histograms, don't they? So there's a time and place for both of them. Let's compare and contrast now that we have two things that kind of look the same. So remember that the bar chart is going to tell you how distributed, like what is the distribution of a categorical variable. Like we've got ice cream cones and things. Let's go back to a bar chart that we made for ourselves. Like we've got a bunch of movies in different studios and we wanted to know relatively how many were made by different studios. And so the width is always the same if you want to think about it that way, but it was a categorical variable. They're not numbered. You can't like assign Paramount to a number. It doesn't make sense. It's a value, and it has some number that we're graphing next to it. It happened to be the count of how many things were made by that particular studio. It has nothing to do with area or anything like that. The bars have the same widths, but those widths are completely arbitrary. It's just how many, you had to make it smaller because we made a smaller graph. We had fewer things in it, you can make it wider. It doesn't mean anything really. Okay? And they can be in any order. The order doesn't matter because there is no ordering to categorical things in general. The height or the length of those bars and the area of those bars, it is technically proportional to the percent that's there. Like it's longer because they're all the same size. It's longer when there's more things in it, and it's all relative to and the area checks out because it's always the same width, because that's just how bar charts are drawn. You're not going to make a thinner bar for New Line compared to Sony or something. That's just not how you draw a bar chart. So it just kind of comes out of the deal. It's always going to be proportional because of that. But we run into trouble with histograms because then we have numerical variables and we can change the widths of those bins, right? Histograms are for the distribution of a numerical variable. Like I've got some numbers, I want to see where they lie relatively. And yeah, now we've also flipped them. The graph is now more horizontal, right? We've got a horizontal graph. That one's numerical. There's no gaps. The bins, you can make them unequal. That's totally fine, right? That just means like we're considering more things all at once. Like how many things are in that longer bin that we're asking about. And again, the area matters, right? The area is proportional to the percent of individuals, the percent of values that were in that particular bin, and the height is how packed it was, because it's always you divide by the width, right? So the height measures the density, how many things are in that bin relative to its width. So how packed is it? Okay, and so that's what you get. Yeah, it's just telling you proportional things with a bar chart, and the width is always the same. With a histogram, because you're going to have uneven bins, you have to be very, very careful. And that's why we spent several slides on the area and the widths and the heights and all that. Okay? Yeah, so that's the difference between the two. I hope that makes a little bit of sense. And now I just kind of want to have us play around with histograms, and that'll be it. Any questions before we do that? All right. So my first question for you is I'm going to give you like something I actually concretely want. I'd like you to please try to make 2 histograms. I would like you to make a histogram to show the survivors of the Titanic and their ages. So pick out only the survivors of the Titanic and show me relatively how many were in different age groups. All right, and you can change. You can make the bins the defaults. You could make them whatever you'd like. But please try that. Please get the Titanic data set loaded and ready. You can go to our code from class to remember how to do all that. Re-download the file if you need to, but that's how I made the histogram of the things, and it's going to look very similar if you want to do it that way. So yeah, try to make the survivors of the Titanic, pick them out, and based on their age, bin them by ages, see relatively how many younger people were ended up surviving versus older people ending up surviving. So do that one. And then also do the other one, do the flip side of that. Pick out only the people who did not survive the Titanic. Pick out the non-survivors where the survival was set to 0. Pick out those guys and also bin them by age. See, relatively, were there a lot of older people that did not survive relative to the younger people, maybe? Like they tried to prefer saving the younger people? Try to figure that out with a histogram. So make 2 separate histograms, one for survivors bin by age and one for non-survivors bin by age. Does the question make sense? Idea make sense? So please try that. Let's see what we get. You can make the bins the defaults. You could also use some A-range stuff and do it the way you'd like. But let me quickly give you all the code we just did. If you want to go to the code from class for our chapter 7 file. Now you should have everything I did today. Yeah. And that's the relevant line .hist, right? So go and get the Titanic table loaded in, titanic.csv in a data folder. I don't already have it from last time. Read it in, pick out just the survivors, and also the non-survivors in a separate one there. That would be a .where condition, wouldn't it? .where twice, one for the survivors, one for the non-survivors, on the survival column. And then do 2 histograms. We based on their age values, and that is lowercase age, I think, was the name of that column. Unless it's backward. No, I think it's capital H in this one. There's lowercase in the picture, though. So yeah, maybe we'll see some interesting results that we can interpret these graphs. And this is definitely going to answer a question that maybe we have, right? This is one way to do all that. So I'll give you a few minutes to play around. We got plenty of time. Mm. Interesting. It is possible that there were just a lot of children, for example, or there were just a lot of old people. So there were a lot of relatively old survivors, as well as old people who ended up passing away. Very possible to see high bars for the same age group in both histograms, but we won't know until we try. Is that going to be the same? Maybe. I'll give you another 30 seconds as a head start. All right, well, my timer pretty much going off. Are there any questions that came up as we were trying this? Were we able to get an interesting looking graph for the Titanic? 2 of them. Let's try it. So let's read in the Titanic data set. I'll just call it Titanic. Table, read table, data, Titanic.csv. So here's my data set. And let's say I want to make my own bins. Let's make it by intervals of like 5 years of age, something like that. Nice small packed bins. I think that would be nice. The way that we figure out like how wide do the bins need to be is, I guess we know, at least from remembering, like there's somebody that was 2 years old on the Titanic. Some of them didn't even have an age, but we'll deal with that in a second. But we have all that. And gosh, what is the last bin? If we're going to go by 5, let's say we'll go by 5. So like this person would have gone in the 0 to 5 age. This person would have gone in the 25 to 30 age. What's the last bin? So let's figure that out real quick. Let's get the way that we can do that is taking the maximum age, right? Let's go find the maximum age in this data set. Titanic dot column age. This gives me all the ages. Some of them we don't know, they're nans. But you can get the max and the min of those. So let's just do both, min and max. You can see that we're going to need a 0 to 5 column already, but for fun, I'll print it out. With a comma, remember, you can print out 2 things. So it looks like somebody was about half a year old, and then somebody was exactly 80. That was the oldest person on the Titanic, was 80 years old. So that means that our bins can go... we're going to need somebody in the last bin. We're going to need a bin from 80 to 85, won't we? So I need NP to A range. I need these bins. Let's start at 0. Let's go not to 80, but 81 by 5s. I think that would work. Or actually, that person who's 80 years old isn't going to end up in any of these bins. What will we do about that? Let's go even farther then. Let's go to 86. because that'll give me between 80 and 85 as the last bin. That biggest, the oldest person would be in the 80 to 85 bin, wouldn't they? Because they wouldn't be in the 75 to 80 because it does not include the last round. It does not include the upper limit. So those can be my bins. And let's keep track of the survivors and the non-survivors now. So that's what I want to do. So let's call them, let's do Titanic.where. It was the survived column, where the survived column values are equal to 1 means they survive. So it's just a bunch of survivors, all right? And I'll call those survivors. Survivors equals that. And then I'll do the same for non-survivors, and that's where the survived values are equal to 0. So that's me getting the survivors and the non-survivors. And now we can do histograms, right? We can do one for the survivors, binned by age. So let's do, the way we say that is, right, give me all the survivors, do a histogram of their ages, right? Because that age column still exists with a capital A. Capital age, do a histogram. If you just said enter right now, it would give you the default 10 bins. Default 10 bins, and then I would be happy. Otherwise, we can give our own bins. Let's give these bins equals np.arange 0 to 86 by 5s. And usually you put the equal sign next to the values for fun. There we go. We get that last one right there. Perfect. There's my 80 to 85. The 80-year-old, there's only one of them apparently, probably. And so this is the age distribution of the survivors on the Titanic. Probably the best way to figure out like what this really means is to compare it to the age distribution of just everybody who was on the Titanic at all, who survived and who didn't survive. But this is still interesting knowledge. It looks like a lot of the very young children, like relatively, a lot of very young children were saved. Teenagers, I guess, didn't get saved a whole lot. But then 20 to 40, that was the bulk of the people who ended up surviving. All right. Then do the same thing for the non-survivors. And relatively, you can see just the fact that there just weren't a lot of teenagers. So this is 0 to 5, 5 to 10, 10 to 15-year-olds. There just weren't a lot of them on the Titanic, apparently. Didn't really survive or not survive. There just weren't a ton of them. But you can see that not a lot of children did not survive, if that makes sense. Which is good. Like the very young children, they were prioritized probably. That's a good thing. And yeah, it just kind of looks the same for the other ages, and so it's just kind of like whoever else could fit in the lifeboat probably was taken and saved. But yeah, that's how you can kind of interpret those graphs. You can always compare this to like what did just like all of the Titanic people, the whole Titanic, what did it look like? Their age groups. And you can kind of see that there were a few very young children, not too many like 5 to 10-year-olds, 10 to 15-year-olds, and then it jumped up a whole lot to like probably adults, 18-year-olds, and then it just gets smaller from there. So yeah, that's how you can think about that. That's that histogram, and you can kind of see that it mimics both of these graphs for the ages above like adults, which would probably indicate that it's just like whoever was available will end up at the top of the ship at the moment was survived. Like there wasn't any prioritization there, but you can totally see this spike here for the younger children versus like how many were relatively on board. That means that they were prioritizing them probably. So that's cool to think about, and you can see that from the graph. Are there any questions about that? So that's a nice way to answer questions that you might have about a data set. I love it. All right, so that's that example. Are you ready for some fancier graph stuff? I want to teach you how to make some cooler graphs with multiple colors. This is equally sized bins with a histogram. You could have made uneven sized bins if you wanted to. It's easier to read when they're the same size usually. If we're good, let me show you how to put two graphs in one. It's called an overlay. So I want to overlay some graphs for you. I've got a weird data set, a cool one. It's called Sun's Heights. So there was a study done about parents and their their sons that they had. If they had a son, they kept track of the heights of those sons, and they tried to see if there was any correlation between like the father's height, the mother's height, and the son's height. These are in inches, I think. Would make sense for them to be in inches at least. And yeah, let's see. Let me show you how to make some cool graphs from this. Like I've got 3 variables here: father, mother, and son. If I want to make a scatter plot, I've got to pick somebody on the x-axis and the y-axis, don't I? I got to say like sons, heights, scatter with son on the x and like, I don't know, father on the y. I don't know, something like that. I can do that. So like if the sun was 70 inches, here are all the fathers for a 70-inch sun. That kind of makes sense. It's all over the place because it's never perfect. It's never exact. Same for the mother's heights. So for a 70-inch sun, the mothers who had those 70-inch suns range from here to here. You see all those like that. But what if you wanted to see both? You could do this. You can say sun's heights.scatter, and then you give the name of the x-axis, and it will put everybody else on the y-axis. Isn't that cool? And I use different colors, of course. Like father is going to be blue dots, mother is going to be gold or like yellow dots. And now you can see both at once. And where there's overlap, it kind of colors them in, kind of blends the colors together. Do you see that? So that's kind of neat. If you just want, like, here's the thing I want on the x-axis. I want to see everything else. Graph everything else, please, for me. That's how you can do that. Okay? Let me show that to you. There's that one. You can do the same thing for a line plot. Let me show that to you. And then a bar chart. So I want to do overlaid every kind of graph we got. So that's an example of a scatter plot that's overlaid. Does that make sense how you do that? Just say what you want on the x-axis, and it will pick every other column, which was father and mother, put it on the y and give them different colors so that you don't get them confused. That's pretty nice. Let's do a different one. I just got a bunch of silly examples to show you. Let's do a line plot. So I need something with chronology. So I've got a table of census estimates for like how many people should be alive right now. The census, you do that and it counts how many people are living in like the United States or something. So here's like US Census estimates from like between 2010 and 2019, okay? And so it's like, here was the census in 2010 of people aged, oh gosh, let me show you what this means first of all. I think, I don't actually remember. There's, yeah, people aged 0 and I can't really see all of these, can we? What's the best way to do this? Census where the age values are 0. There's 3 of them, and how this works is, I think probably sex 1 is male, sex 2 is female, and then sex 0 is their addition, their sum. So those are all, like, if you want all the 0-year-olds, you do sex 0. Could be anybody, okay? So that's the census table. That's kind of how you read it. So like here's the actual census values for 0-year-olds. Here's the estimate, because people sometimes forget to do things or don't fill out the census. And so there's estimates from it. And yeah, let's talk about a few of these things. So census, remember that dot group? I can show you all the sex values again. It was 0, 1, and 2. And there's a bunch of them. There's all the way to like 102. The age goes up to, I think it just goes up to 100, I believe, and keeps track of all the people of all those different ages, and the males, the females, and just anybody combined. So there's those, and those are the different values of the sex variable, 0, 1, and 2. And notice again that these values for sex are 0, 1, they're numbers. They're numbers, but they don't have anything to do with math. So again, sex is a categorical variable, even though it's a number. Crazy. So we have that, and so let's do a line chart. Let's do a line plot with the census data. So let's pick out only the children. So census where the sex is 0. So every person. where also the age values are below 19. So let's say 0 to 18. All right. So let's call those kids. I guess we could do, let's do below 18. Those are all the children. So kids in the US. And here's this table. So you got a bunch of 0-year-old data, 1-year-old data, 2-year-old data. So all those estimated populations of the people of those ages. And let's select out only the ones that only the years that we care about. Let's select out the population estimates for 2010 and the census population estimates for maybe 2014, 4 years later. So this is what they're thinking is going to happen, running their models. So here's a bunch of different values for the 0-year-olds, 1-year-olds, 2-year-olds, all the way to 17-year-olds. So let's call that the kids table again. And then let's also do, let's relabel these columns as well. So I can say kids.relabeled. Let's relabel I can relabel multiple things at once by putting them in arrays. Relabel both of these guys, pop estimate 20, because they're so long to type. These guys to just call them in order, 2010 and 2014. That would make it easier. And so there's what I've done. I just renamed those column labels. This is a great example of just a bunch of stuff right now. I'll call that kids some more. And then, yeah, that'll be my table, I think. There's my kids table. All the 0-year-olds, 1-year-olds, 2-year-olds, all those things. And let's see. Oh, I forgot age. Sorry, let's keep the age in. Age is fine. So age is how many 0-year-olds they think are going to be in 2010, how many 0-year-olds they'll think existed in 2014. They're trying to predict the future. And if I say, remember for a line plot, stop plot. If I plot all the values based on age on the x-axis, again, it'll do the same thing like a scatter plot. It finds the other two values, the 2010 column and the 2014 column. It will use those as the y values. And it will do them separately. So that's what I wanted to get to. So all the 0-year-olds, all the 1-year-olds, and this is another good case for a line plot. It's kind of connected, right, by age. You see that there's a little bit of one thing comes after another. It's going to sort. So that's kind of neat. How many? Because I guess the things are a bit out of order. This is how many? There are the 3-year-olds. There are the 2-year-olds. It's doing the axis automatically. It thinks that there's going to be that many 3-year-olds in 2010 and that many 3-year-olds in 2014. You'll think that people are going to stop having children or something. But one thing you can see from this plot of all the census values is, do you see how the 2014 data looks a whole lot like the 2010 data, but shifted over a little bit? Just shifted over to the right. And that would make sense, right? Because all the kids that were this age in 2010 are going to be that age in 2014, won't they? Well, that's why we can see that from the graph, and that's pretty cool to think about. And then it's going up a little bit more than that. You see that the graph has been shifted over and up because of immigration. That's a thing that happens, and that adds to our population. So it's almost the same graph pushed over by 4 years. That's pretty cool. Is there a question? Yeah. To there? Oh, I just add it to the select. I'm gonna put it back in. We're gonna need that too, because that's the x-axis. Yeah, and it's just fun to think about because you can stare at this table all day long and you won't notice that until you make the graph. That's very powerful and very, very cool. So yeah, there's age data, and that's just a plot of multiple values. You say what you want on the x, and it'll put the other things that you had, as many as there are, all the other columns will be y values for that x value. Cool. Any questions about that one? So that's an overlaid line plot. We're we got to complete all three of them, right? Let's do a bar chart, an overlaid bar chart. Why not? That will be one of the last things of these examples. Then I have a few other weird things to talk about, and then one more question for you. So, okay, let's do, for fun, let's read in the Pokemon table. That's what I'll use as my example of a line plot, or of a bar chart that's overlaid. Table, read table, let's do Pokemon. Boop. So here's all the Pokemon, and I'm going to do some weird things to this table that you don't have to understand. I'm going to go to my code for that. Because it's a lot of typing, but it gives me a cool thing that I want to show you. It helps me make a very cool bar chart with a bunch of things in it. These guys. So I'm stealing from my notes. I did not copy for some reason. There it goes. So don't worry at all about any of the things I'm typing here. There's some weird things involved. It's a very wide thing. But what I've done is, for every type of Pokemon, I have made a count of how many were in Generation 1 of that type, how many were in Generation 2, Generation 3, and Generation 4. So there are 12 Fire Pokemon in Gen 1, only 8 Fire Pokemon in Gen 2, things like that. All right? And so now I have a categorical variable, the type of Pokemon. If I say, and I made this table called Gen Types, if I say bar H to make a bar chart, and I use the type 1 categorical variable, I can say what I want to be its values. I can say, like, use the Gen 1 count. That would totally work. And I would make a bar chart like that for the Gen 1 counts of all these types. But if I omit this second thing, just as usual, it will use every other one that it can, that's a number at least, to make a bar chart. It'll make 4 separate things per Pokemon type, 4 separate colors. Look at it. It's so cute and small. And so that turns it into this table gets turned into this bar chart. And I hope you kind of see it. So it's like, you can see now the relative amounts of bug Pokemon were equal between 1 and 3, but it went down in Generations 1, way down in Generation 4. Crazy. You can see that Dark-type Pokemon did not exist in Generation 1, but there were a decent number of them in Gen 2. That's cool to think that there were no dragon Pokemon for some reason in Gen 2. Maybe they thought they had enough. But you can see the relative amounts, and it looks like water Pokemon are very, very highly represented in the Pokemon world. I wouldn't have known that until I looked at this graph. All right, so that's just an overlaid bar chart. Any questions about that one? So it took this table, there's some fancy things that I did to generate that table, but it's going to use different colors for every one of those numerical values. You say, what's the categorical thing? And then it uses every other numerical column to plot on the bar chart. Those are the numbers associated with those categorical variables. Cool. So yeah, that's just how you overlay things. You say what you want on the X, or what is your categorical thing. That's pretty neat. Yeah, before I get to one last example for you guys to play around with, I have my standard miscellaneous things section. And so, dun, dun, dun. I need all these things, and yeah, do I want to show that to you? I guess I could. Yeah, let me do it this way. These new 3 things: matplotlib inline, import matplotlib pyplot as PLT, all those fancy things. Let me re-explain them because those deal with drawing stuff. So let me type these out again. So matplotlib inline means every time I make a graph, put it in my document. Don't like make a PDF and export it immediately or something. Put it in the document so I can see it after I press Shift Enter. The type of the library that handles the plotting is called pyplot. It's in the matplotlib library. And usually people import it as PLT, but your book imports it as plots. They'll eventually ask you to use it, and they've imported it as the word plots. So let me save that for you. Your book imports it as plots, but most people import it as PLT. I like to import it as PLT. But I'll just call it plots now. And then this changes the colors that it chooses by default. It's using the 538 style. That's from a website. And so let me make just a little table that I can graph stuff with real quick. So I'll make a blank table with a couple columns. I'll make an X column and a Y column. Why not? So X is this. 1, 2, 3. And then the Y column can be 4, 5, 6. So that's my table T, T. And so I've just got like X, Y, 1, 4, 2, 5, 3, 6. There's my table T. And I can do a scatter plot on the X, and it chooses the Y by default, is the one other thing. So this is the default way that it makes a graph for you. It's kind of like spread out as much as it can between the lower values and the upper values. It's going to kind of like zoom out as much as it can. That's the default way of making your graph. You can control that if you want. Let me show that to you. That's something that you'll eventually want to do. So here's the order. You always want to make your graph as usual. All right. So always make a graph first. So you still always have to say t.scatterx, but the things you can say after it can change how it draws that graph. So the default is that, but if you add things here, using the plots variable, I'm calling it plots this time. If you say plots dot some stuff, you can control how the graph gets made. You can give it a title. You can say plots dot title, call it something, put it as a string. So you always make the graph first and then put stuff on the graph next. It's like this gives it a title. It says, "Hi, Mom," now. Cool. All right, there's that. You can also change what it chooses to be the extremities of the axes. So by default, it chose from 4 to 6 for the Y and from 1 to 3 on the X. So it's like it's stretched out. It's not even perfect anymore. It's not like they're not even widths. It's stretched in different ways, which is weird. But you can change that. You can be like, all right, plots, your Y limits, Y lim, you say, let's make them be from -5 to +10. And then we'll do the same for plots.x limits. Let's make those to be from -2 to +20, just for fun. So you can put whatever you want there. And now the graph looks like this. See how the Y is changed to have these values, and the X values have changed from here to here. So you can change the way the graph looks, and like here are the plotted things again still, but they're in a different place because we've changed the way the graph looks. Does that make sense? That's just how you use that library. And you'll notice that you run into a slight issue. You see this thing printed out to you as well as the graph getting made, because this last line gives back the answer of like what you just set the X limits to. Usually you just want to draw the graph. And so if you put a semicolon on the last line, because by default it's going to print out the answer on the last line, right? Whatever was there. If you put a semicolon here, it prevents it printing out that answer of that last thing by default. Prevents the default output of the last line. So now you don't see it because I put that semicolon there. So yeah, that is more or less what I wanted to say about those things. Are there any questions about how to control your graphs like that? That's just some stuff that you'll need one day in an assignment. But now you've seen it once. All right, if we are good, I have one last question for you guys to play around with and try new things with. Let's talk about our serial data set. I love it. So try to, I think this time we can play around together. Make sure to do attendance if you have not yet, but let's go on to the written nice page, please. And if you'd like to get together with the people sitting next to you, that'd be perfect. Try to brainstorm and come up with some ideas for how to look at the serial data set. You can use any of the things we talked about. You could make bar charts. You could make, what could you make? You could make line plots. You could make scatter plots. You could make histograms. List some ideas that you'd want to see for the things, the variables in the serial data set, and try to come up with some of those and write them down. And then after you've listed them, try to make them on your own, and I'll do some of the ones that you do too, just in case you can't figure them out. So like, I want to make a histogram of the distribution of the sugars in the cereals? Like that's the thing that you can ask about and try to do. So try to write down your ideas first, and then I'll eventually get to some of them. But, write down your ideas and then try. Try and ask me questions. You can't figure out how to do what you just said you wanted to do. You got cereal information, you got sugars and proteins and amounts of vitamins, serving sizes. I think histograms would probably come up a lot, right? Where it's like, all right, what's the distribution of protein, the distribution of calories, things like that. You can do it by shelf too. It get really complicated. But remember that you can extract things. You can do dot wheres. You can get like, give me the cereals on shelf 2, the ones that were extra sugary, right? Let's see how the distribution of the calories there compares to the sugars to the cereals on shelf 3. That's something that you could be doing. So yeah, write down your ideas and then try them, please. And I'll give you a head start, and then I'll try some of them too. Oh, and let me quickly upload all the stuff that we did today, just in case you wanted to look at any of that. So now if you refresh the chapter 7 page, the chapter 7 file, you have everything we've done so far. It might be fun to do like a bar chart of like what's the average calories in each cereal split up by manufacturer. Like, or some manufacturers they tend to have more sugary cereals or more higher calorie cereals. That might be cool to try. Yeah, write down your ideas and then try them too. I'll give you a couple more minutes of a head start, and then I'll do some of them too. Interesting. Well, it's fun. All right, I want to try some now. What are you guys thinking about? I have my own ideas too, though. But let's do yours first. Anybody do any cool ones? Did you have any questions as you were trying them too? So you make histograms, bar charts, line plots, scatter plots. Let's see what we were thinking. Well, first let me actually plug in the serial table. Let's get that first. We'll need that. And then we'll take a look. Serial equals read table in my data folder. It's called serial.csv. It's not that one. Tool. All right, so here's all the serials. What should we do with them? Yeah, let's do, I like the idea of a bar chart. Let's do bar charts of different cereal flavors or sugars. Yeah. Maybe, so bar chart has to be categorical. So I would say maybe flavor, we could use manufacturer. I think that would make the most sense to me because that's your categorical variables are the name of the thing, which is always different. So you can't really use that for anything useful. You have the manufacturer, which some of them double up. Like you have a bunch of Kellogg's, you have a bunch of General Mills, like those, that's useful for some things. And then there's like type cold or hot cereals. I think there were only 3 hot cereals in the data set though. So it's probably manufacturer is the only thing that you can usefully make a bar chart with. So yeah, let's try with that. I'll have to cheat a little bit if we want to do this though, because if you do serial dot bar h and you give it like the manufacturer, it's just going to do some weird stuff because it'll find some non-numerical things. What do you want to put there next to the manufacturer? Let's go to the documentation page first. Let's learn how it is. And feel free to add more ideas. Let's see. So I want to do dot bar h. What I want is I can give the categories or I can give the values that I want per category. We'll figure this out together. If we want maybe sugars, was that healthiness values? We can do, yeah, maybe like the sugars for each manufacturer, or just like the numbers of each manufacturer. Let's do a few things. Bar charts could be good for those things, but immediately, maybe not. Like we can do sugars or something. Immediately, it's not going to give you what you want. We have to do this kind of grouping because you see how it's like it does a bunch of K's next to it. Like we want one K value. It's doing it for every cereal right now. We're seeing a bar chart for the sugars values of every cereal. You got to bring them together first if you want to do it this way. So you could do cereal.group by manufacturer, and I'll teach you what group means in the next chapter. But by default, what grouping does is it'll give you the counts for all these different manufacturers. And then you can do a bar chart of that. Bar H of the manufacturer, because then the only thing left is the count. And this will tell you how many were Kellogg's, how many were General Mills, whatever these things actually meant. So that's one thing you could do a bar chart with. But you could also, when you group, I'll tell you the secrets one day, but when you group, you can supply what you want to do when you're grouping. By default, it's trying to like bring all the Kellogg's together and count how many there are. But you can also say like, you know what, bring them all together and take the average amounts of things, and everything that's numerical, it'll do that. So like, here's all the average calories for Kellogg's cereals. They made a calories average column, which is so cool. And so then you could do like bar H, the manufacturer, and let's do calories average. So this is the average amount of calories for Kellogg's cereals, for Post cereals. They're pretty close. This one seems to be a health cereal, probably. Not a lot of calories in whatever N was. I don't think it's Nabisco. It's something. Whatever N happened to have been. which is cool to think about. So I like that. So that's one way to do stuff with bar charts. And yeah, let's do the other one, distribution of potassium. I like that idea. So let's if you want to find a distribution, usually it means, let's go back to the serial table. Usually that means you want to go and ask about a histogram, right? Because here is the potassium value in a 100% bran cereal is 280 milligrams probably of potassium. We are probably never going to see the number 280 ever again in this data set. And so what we'll do instead is bin. We'll do bins of different amounts of potassium so that maybe if there's a 285, it goes with the 280. And so you can count them that way and make an actual bars on a chart. So that's a good use of histogram. So let's do it that way. I do like serial dot. Let's do a histogram of the potassium values. And you can get the default bins if you want. So here's the default bins. It looks like it goes up to like 325-ish, maybe 350, almost in normal amounts, but you can see what's there. It looks like the highest range where there's amounts of potassium, it's like between 30 and 60-ish or something. So like that's the normal ranges for potassium. You can see what those bins were if you do dot bin. Like what in the world were the default bins for potassium? Serial dot bin potassium. It looks like that second one where there were the most things, like the most crowded bin, right, was between 32.1 and 65.2. There were 21 cereals in that category, which is weird. Like that's in a weird spot. We can show all the bins with dot show. Looks like it goes up to 330 for some reason. But you can also choose what bins you use. You can be like, all right, you know what? I don't like those normal bins. I want to make my own. Let's say bins equals np.arange. Let's go from 0 to let's see, 0 to like I guess 330 is the last one. 0 to 350. Let's go by 50s. How about that? And then you get this, and that looks like it's easier to read, right? You know that this is the 0 to 50 milligrams of potassium. This is the 5100 milligrams, I assume, or grams of potassium. I have no idea. One of the two. And now you can see like it's less likely for the cereals in general to have a lot of potassium, apparently. That's cool to think about. I like that. Are there any questions about that? Does that make sense? Yeah, so that's some ideas with histograms. We could do some, let's see. We could do some scatter plots. That's another thing that would make a lot of sense to want to do scatter plots. Like something with rankings is a good idea. Maybe we could do take the cereals and we do a scatter plot of let's do like rating versus how many sugars. Like I still don't fully understand what rating is. Let's try to explore what that rating value could be, because even the people on the website where I got this from didn't fully understand. So let's do sugars on the X for each cereal, and then the rating value on the Y. That's a scatter plot. And it looks like when there are more sugars in the cereal, the rating tends to go down. Interesting. So I have a feeling like rating is not like how many people liked it. It was probably a rating that was calculated by how healthy the cereal is. That's what I keep thinking about when I saw this last semester and this semester. That's what it makes me think. And you could have graphed this in the other way, right? And you could have put them on the other axes. You could have been like rating on the X, sugars on the Y. If that makes more sense to your brain, that's totally fine. It looks like as the rating goes up, the amount of sugars goes down. So that's the same graph, just flip-flopped. That's cool. I like that. Let's see. And yeah, you could play this game for a lot of things. You can be like, let's look at the different amounts of sodium in the cereals. Like that's another thing that people tend to avoid, right? If we look at the sodium amounts, let's do maybe a histogram of those. So by default, if I were to do a histogram, what were the bins I would get? So if I said serial.bin sodium, they just spelled it out with a lowercase s. Like here are all my bins. Dot show, see them all. It looks like it goes up to 320 by increments of 32, which is kind of nice. I guess that's a computer sciencey number, but probably not a number that people like to think about usually. We can make our own bins. You can be like, all right, if 320 is the max, if you weren't confident about that, by the way, you can be like, all right, give me the serial dot column for sodium. What should these bins go up to? Give me the maximum thing here, max over all these. 320. So that is 320 correctly. So let's do it this way. Let's do like serial dot give me a histogram of the sodium values where the bins are not by 32s, but let's do np.a range where we start at 0. Let's go up to like 325. Let's go by 25. So that would be a good ending point, I think. And so that's an easier way to make the distribution. And it looks like, surprisingly, a lot of the amounts, most of the cereals had sodium values that landed between, at least proportionally, this is the most packed bin, right? Proportionally between 200 and 250. I think it's probably milligrams of sodium, right? So that seems to be the sweet spot for a lot of cereals. Interesting. I would wonder how that varies by shelf. That's another question that you could ask. You could do a dot where, pick out different shelves, see what's going on. But yeah, things like that. Those are good questions and good thoughts. Yeah. Let's do one more. Any other ideas? I'll show you one that has like an overlaid graph. I think that would be a useful thing to try. Let's do an overlaid graph. Maybe an overlaid bar chart with this kind of idea that I was doing up here. Like this weird way of grouping things. It gives you the averages in a bunch of different ways, which is cool. So for each manufacturer, here's the average protein for Kellogg's, the average fat for a Kellogg's cereal, because MFRK was Kellogg's and stuff like that. You can do a bunch of these. You can do a few of these. You'd be like, all right, do this kind of grouping, and then select out only the things I care about. Let's do the manufacturer, of course. Give me the sugars average, and then give me maybe like, what's the opposite of sugars? What's health related? Let's do like the fiber average. Something like that. So I've just selected out some of the things I care about for each manufacturer. And then let's do a bar chart by the categorical variable. That's the MFR, the manufacturer. And so for each manufacturer, A, G, K, all those values, I'll see sugars values and fibers values. And so now you can compare kind of two ideas at once for each manufacturer. It looks like General Mills cereals are horrible for you. They, in general, have a ton of sugar and not a lot of fiber. That's crazy. Whatever P was, I think it was like Purina, which I don't know if that's a brand that exists for cereal anymore. Or maybe it's Post. Maybe Post cereals. Probably that's what it was. Post cereals. They have a lot of sugars, but they have at least more fiber on average than General Mills. Crazy. It's on the same level as like Kellogg's have on average fewer sugars. That's maybe better. So buy those for your kids. What's the healthiest one with the least amount of sugars and the most amount of fiber relatively? It looks like whatever N was. I don't remember what that brand was, but that's got to be a health food brand. We've seen a few things about this N manufacturer that makes me think that. So yeah, that is an overlaid example of a graph, and that shows you some things. If you have both of those together, it shows you like relatively how much does this manufacturer care about the health of their cereal, how healthy it is for their consumers. And that's data science. I love it. All right, I think that's a good one to stop on in my mind. Are there any other questions or any other things we want to try before I let you work? You see how I made all these and thought about these questions? That's the important part. I want you to be able to formulate them too. So that's pretty cool and pretty fun, I think. I love it. So yeah, the last thing I want to do, I promise to stop that, is we have one new assignment that I can assign due dates for. It's homework 3 is the one that depends on this chapter. That's the last thing it needs. So let me go set a due date for homework 3. Chapter 7 is what it depended on. And let's look at the dates of other things so that we don't clash. So it looks like, yeah, we've got a free slot on next Friday. So lab 2, let's do today, homework 2, then lab 3. Let's do homework 3 due on Friday. That'll keep a good pace, I think. So not a week and 2 days from now, homework 3. And that'll be the 13th. And yeah, I think that is all that I need to record. So I'll stop the recording.